Be seated. We must start. Today, the first speaker is Mr. Sophocles Sotiriou, the President of Balcan Physics Union. Dr. Sophocles Sotiriou is a Greek physicist, researcher, and science educator. He was born in Athens. He studied physics at the National and Kapodistrian University of Athens, and later completed 2 PhD degrees, one in high-energy astrophysics and another in science education. He has worked at CERN, the National Center for the Scientific Research Demokritos, and the University of Athens. Since 1998, he has been the head of the Research and Development Department of Ελληνογερμανική Αγωγή. His work focuses on using advanced technologies and innovative methods to improve science education. Dr. Sotiriou has coordinated many European research projects and has published extensively in the fields of science, technology, and education. He is also a member of the European Academy of Science. His career combines scientific research with his passion for the science more accessible and engaging for students. Mr. Sophocles, the stage is yours.
So, good morning. I hope you had a nice evening. And we are starting today. I will try to start exactly from the point that we have closed the discussion yesterday during the keynote talks. So I have this quite complex, I would say, title in my talk, AI-enabled inquiry-based learning pathways. So I will try to demonstrate that also in the field of education, and then especially in the assessment, which is a very crucial field, AI could support significantly our work. So I'm going to discuss how we will try to solve a very crucial problem. Don't forget, we have discussed so much yesterday about we are trying to use AI in cases where we are facing really quite complex problems or difficult situations to solve specific challenges. So here we have another important challenge that I'm going to talk about, is the assessment of the collaborative problem-solving competence in a classroom setting. To make it more simple and let's say try to connect with the issues that we have yesterday. Yesterday we have tried to present to you cases where AI is helping us to see more clearly the tiny signals of particles, the tracks of the neutrinos, and so on. Here we have another very demanding case. Can AI see students thinking? Can we use AI to assess students' understanding during the educational process? So how AI agents that are activated during the lesson could help us to recognize specific competencies of the students. I have to say I was a bit surprised from this finding yesterday at the end of the third keynote from Thrasivoulos. The question was, where do you think that AI will have the greatest impact? And the science research outperform all the other fields, but outperformed significantly the very first one. I believe that Thrasivoulos had put this as a very first because he was expecting really to see it a bit higher. This is also what we have discussed during the dinner. But education and learning seems, according to your view, not to be affected from AI. Is there a reason for this view? What do you think? Yes, please. Perfect. Yes? So I will try to present to you that also in education we have very complex issues to solve. In fact, in many cases we are speaking for the black box of education. So it's like a box, the students are entering, then after 12 years of schooling in most countries, in other countries after 13 years of schooling, we have the young, let's say, the young people who are entering the world of market or research or academy and so on. And they must have some basic competence in order to operate as citizens. But in between, we don't have a clear view of what is happening, how these competencies are developing. Because our assessment systems, the current assessment systems are making, as we say, only summative assessment. So they are assessing the knowledge, first of all. The skills, I would say, we are facing significant problems to assess these skills. But in principle, we have to be able to track, to monitor the development of the progressive development of these competencies, because only then we are able to make sure that the young people have the necessary competencies in order to perform in the world after schooling. So, yes, I was also surprised that according to your view, education and learning, we don't expect to see significant impact from AI. As I said, I will devote the next 40 minutes to try to convince you that also in education there are crucial problems. I have mentioned yesterday that we see a significant decrease in the number of students who are attending the physics departments. So clearly, for us as physicists, and especially for, let's say, for people who are working in the field of science education, we would like to see this situation changing. We are not, clearly, we are not happy with this. It's because of the school, it's because of the curriculum, it's because of the teachers. But in principle, we would like to see in the near future significant changes in the science classroom. So that's why we are envision the science classroom of tomorrow. Assessing complex competencies is the second issue because they are a very important parameter that has to be integrated in the science classroom of tomorrow. I'm going to present to you our first efforts, how we can combine learning and assessment in the same framework. So not to have individual tests, but the assessment to take place while students learning, while students are working on the specific tasks. inside their classroom. And I will provide some practical examples, also from the work that we have done the previous years here in this summer school, working also with students like you. So the story goes back in 2006. 2006, the European Union is publishing this policy document promoting inquiry learning. Inquiry is, as it says here, a renewed pedagogy. It's not something that we invented in 2006. Inquiry learning is there for many, many years, but it has not really implemented in the school classroom. And maybe it's not possible really in a very tight curriculum of 45 minutes to implement what is expected, let's say, in order to call an instructional approach inquiry, to offer to the students the opportunity to make experiments, to make hypotheses about the outcomes, to design models, how the experiment or the phenomenon is working, analyze the data, come up with conclusions, have the possibility to make numerous mistakes, and repeat the cycle again. So this is not happening in the science classrooms. But this was, let's say, the policy guideline of the European Union back in 2006, and significant amount of money was devoted to this effort. So numerous researchers have worked, have tried to convince the policymakers that things have to change in science education and in physics education. In fact, nothing has changed in the science classrooms across Europe. It's not only in the Balkan countries. I will try to show you that in Balkan countries maybe the problem is even bigger than the other European countries, but still the problem remains for the whole Europe. And according to my view, this is why we see this significantly decreased, let's say, number of students who are following careers in physics. So about 20 years later from this policy, in fact, nothing has happened. And this demonstrates how difficult is this field, how traditionally, let's say, operating is this field of education that is, let's say, that the system itself does not want to change. So still we can have our visions. Still we can thinking of a classroom that on the top you see the traditional classroom. Below we see the science lab where different experiments, activities, researchers are working, trying to discover new things and so on. And in between, we try to see this classroom that we are thinking about. So a classroom where collaboration is important, where we assess critical thinking and problem solving, where students are developing academic mindset through the whole process, through the experiment, through sharing their results, discussing with other students, exchanging results, and getting all the necessary competencies for lifelong learning. So this is what we have in mind, and there inquiry learning is playing a significant role. But what is the main outcome of inquiry? When we are implementing inquiry, in fact, we are trying to develop the problem-solving competence of the students. So in this classroom, I will not discuss about the content. I will not discuss about the innovative activities, how we can enrich the curriculum, how we can use, let's say, digital technologies to enrich the experience. I will focus only on the assessment in this talk. So we have to stop to try to measure what is easy to measure in the field. We have to focus now on more complex assessments. I can very easily come at the end of this summer school and ask you, did you like it? Are you going, let's say, to recommend this to other students? Are you planning to come next year? And so on. These are very, very simple questions, and I can very easily get answers, positive or negative. But the process is very simple, is very traditional. It's going to give me a rough idea about the success of this course, of these activities that we are running here, but I will not be able to see the real impact, the long-term impact of this activity. So it's very important to design a next generation of assessments integrated in the learning process. So the students are not having a questionnaire at the end. They don't have a test at the end just to see if they have learned better and so on. But it has to be integrated in all phases of the learning process. And this, of course, it will give us a unique opportunity to collect data from different resources and prove the overall concept. So this is how the technology-enhanced assessment, let's say, developing. We have the traditional assessment that is based on tools like I have a Google form, I'm collecting all the data. We are just replacing, let's say, the paper and pencil assessment. So I'm able to analyze the data, to collect the questions. You have seen yesterday some examples with a tool that Rasivulos collected some useful data about your views about AI and your understanding about the whole keynote talks session. But then we have to move to a bit more complex level. And there we have technology-enhanced stimuli and reform and response formats. So we are integrating some aspects that are related with the learning experience itself. So the question is not there just to assess in the specific moment the level of learning or the competence development, but it's there to support students' learning and competence development. So the system is making a decision that this student probably needs some support, some scaffolds there in order to proceed to the next task, or is identifying a very important issue in science and physics education, identifying critical misconceptions that the students are bringing with them. And we have really to devote significant time to cope with them. Otherwise, we are building a whole castle, with not on stable ground. So we have to focus on specific issues. We have to design the tasks in order students to be able to work on with them. And we have to collect evidence to demonstrate that there was significant impact of this intervention. And we are, let's say, in the near future, we hope, also with the support of AI, that we will design a system where the assessment is embedded to the learning process. So in principle, you will not understand that at the same time, while you are performing a task, you are also being assessed. You are not being assessed just to get a mark at the end, but you are being assessed in order to see the level of your proficiency in specific competencies and try to support this further. The specific example. In 2015, PISA is publishing an instrument to assess the collaborative problem-solving competence. This is following, let's say, the publication of 2012 for the creative problem-solving competence. We are always speaking for the competence of an individual, independently if it is, let's say, if it is called collaborative or creative. We are always referring to the competence of an individual student who is performing a task, but in the real classroom environment, this activity is taking place in collaboration with peers. So to simulate this human-to-human interaction when the students are working together in an experiment is a very, very complex task. According to my view, it's more complex than reconstructing the track of the neutrino and the muon, as we have discussed yesterday. So to fix this, in 2015, PISA is introducing the concept of conversational agents. As during a test, I'm not able to have students to collaborate because the noise will become significantly higher, I'm creating a character, the conversational agent, that is collaborating with the student to solve the task. So this is the context where we are trying to measure the collaborative problem-solving competence. But it is really very, very difficult to simulate this real-life context with this test. Okay? So, in fact, we were somehow blocked there. We were not satisfied with the results from this study. That's why the study was never repeated, because we had to find tools that are helping us to create a more realistic environment for assessing this competence. And now, with the existing technology, we are coming back to this. And in 2029 test, the problem-solving competence is coming back to PISA. And PISA experts are working towards this field in order to enrich the test with AI-enabled conversational agents. Now we have the technology, we have the chance really to revisit this concept and try to see how we can assess this competence. To do that, we have to describe all the aspects of the processes and the factors that are affecting the problem-solving competence. This is from PISA 2015. The framework will remain the same. So we have to work on the student's background, prior knowledge, characteristics, their motivation, cognitive ability, critical misconceptions. We have to identify the core skills, collaboration, problem solving, and so on. And we have to define the context. We have to see how we can integrate in our lessons all the necessary characteristics in order to see the development of the problem-solving competence. If I'm giving a lecture, I'm just, transmitting information. You are the passive receivers of this information. I don't expect really to see any development of the competence. So we have to assess the competence development when we have the specific tasks in place, okay? When there is experimental work, when there is collaboration, and so on. Otherwise, we can measure before, we can measure afterwards, and we don't expect to see any change. So we have to describe all the task characteristics, the task type, the setting, the domain content. We have to see the different roles, and we have to design really a context where all these things can present it. We have also the exact way how to evaluate, because the problem-solving competence consists of different partial abilities. For example, students have to be able to explore and understand a phenomenon or a concept. They have the ability to represent and formulate hypotheses and create models. They have to plan and execute an experiment. They have to monitor, analyze, and reflect on the findings. So these are the key partial abilities of the problem-solving competence. And PISA defines also the specific weights that we have to take into account when we are measuring the overall competence. So maybe you are not convinced up to now for the importance of the problem-solving competence, but maybe this table will help you to see the problem. Here in this study, this is from 2015, PISA results, problem-solving competence, and unfortunately only 3 countries from the countries represented in this room are there, but they have some very common characteristics. This is Bulgaria, Cyprus, and Greece. So here are the levels of proficiency of the students participated in the test. Here it has the levels of proficiency. Here is the first level and below first level, level 2, level 3, and level 4. These together, below level 1 and level 1 are representing the so-called low performers, students who have a low proficiency in solving a problem. Level 2 and level 3 are representing the moderate proficiency in solving problems. And level 4 are really the ones we call reflective problem solvers. So students who not only understand the problem, but they have the ability really to see how this is implemented in real life. So in Greece, about here it says 31 plus 10, it's about 41% of the students participated are low performers. Very big number. 4 out of 10 students in Greek classrooms are low performers. About 56% are moderate, and only 2% in our classrooms are high performers. This, for policy, let's say, makers, have to be a shock. Here is also Bulgaria. In Bulgaria, the situation goes even higher. 34 plus 15, it's about 50% low performers. And in Cyprus, about the same percent, 50% low performers. So this was really a shock for this. This was a test that was realized with thousands of students, 15 years old, on a specific 3-hour test, fully computerized. The idea was how the students can develop a digital aquarium. And an agent, a conversational agent, was used in order to support students during the task. So, can AI help us, let's say, to improve this situation? Can, for example, AI help us if we integrate all this process in a lesson, try to track the performance of the student? This is the key question. This is the test environment from PISA 2015. Here, this is Abby. This is the conversational agent. And the student, in principle, it's the student who participates. and they have a discussion. Here in the screen, it's not so easy to see the discussion, but as I said, the whole, my presentation is available, so you can also have links to see how this was developed, and also to follow the discussion between Abby, the conversational agent, and the student. The same year, back in 2015, with the Ministry of Education here in Greece, we are trying to make a similar experiment. Instead of having a specific test, a 3-hour test, completely isolated from the lessons, we are integrating these kind of lessons with specific tasks in the school curriculum at the 3rd class of gymnasium with 15 years old. At that time, more than 12,000 students participated in this study that took place in Greece. And we get about the same result for the low performers. So the only change here is that the lessons are taking place, the assessment is taking place in a real life setting, in a real classroom, not in an environment where the students are making a test. But we see a significant decrease to the moderate population, and significant decrease and significant increase to the high-performing students, only by introducing inquiry. Only by introducing. But in order to do it, it had to be somehow imposed from the Ministry of Education, because otherwise it's very difficult to implement inquiry in a normal school classroom, in the normal curriculum. So the test was there. We were quite successful in increasing the number of high performers, but still able to decrease the low performers. So significant further work is needed. So the process that PISA is following is called evidence-centered design. Again, yesterday we discussed about the importance of the user-centered design, that the users have to be part of this, and as it was presented in the keynote, users have to be part of the development of the new tools. The same applies here. So we have the key area, the domain, which is the PISA problem solving. We need to define what do we expect to see, the student model, which are the variables and which are the different levels of proficiency. We have this, the levels as presented. We have the high-performing students, the moderate students, and the students who demonstrate relatively low proficiency in the problem solving. So we have all that. Yes? This is the design process. In order... Yeah. Please repeat, because it was not so clear. Here I'm describing the development process of the instruments, okay?
Yes, I wanted to ask something about the previous topic that you were talking about, the PISA test.
This?
Yes, here.
Yes.
So, as far as I know, this test is, I'd say, controversial in Greece, at least for many people, because they believe that it is quite stressful to students. However, how can we say that we want, on the one hand, to improve the scores of our students and its performance, while on the other hand, we are criticizing the whole existence of this test?
You are referring now to the policy, let's say, the overall policy against the PISA testing?
Yes.
Okay, but this is, let's say, something that, you know, there is always the following issue. When you see the results, you say you have two options, let's say. One, to consider these results and try to see how you can improve. And the second, to say that this test is not appropriate. Okay? So I believe that the test is appropriate because it's a test that is working for all countries, and in principle, it's a process that is measuring. Please don't mix this. This is the PISA problem-solving test. This is not the science test or the math or the literature test that is implemented every 3 years. This took place only once, and the data were published in 2015. Okay? And because it was so complex, PISA has never come back to implement it. But now, they are making a new effort using the AI technology to support the interaction between the student and the machine. Okay?
Okay, thank you.
But the process on how you are going to deal with the finding is, one is to ignore it, to say this has nothing to do with me. In principle, this is what is happening in Greece. And on the other side is try to improve the test and demonstrate that in principle it is capable to measure the specific competence. I'm not saying that it is an easy thing. Okay?
Okay, thank you.
All tests have, let's say, their pros and cons. Here we are trying to simulate a real-life situation in the classroom, in experimental work. So to simulate all these aspects is not so easy, okay? Especially in the traditional tests, there is like a tree structure, you know, from the moment that you are receiving a negative score in the first phase, then your track, your path, more or less is fixed. So we need a more dynamic process. And this is what we are trying to do here. I will present you here, we have a very simple case. The practical example that I mentioned about is about the pendulum. And we will see how we are able to track, to monitor the path of different students while they are trying to solve and work on a very simple experiment using the pendulum. Okay, so there is a whole process. This is the new thing, how we design the tasks, how we can integrate in our lessons all these aspects. Task format, it is a non-interactive problem, it is an interactive problem, it's an immersive problem integrated in the process, the test features, and the different sources of data. We have, let's say, all these tools now available. We can use a variety of tools to help us to improve the experience of the student, simulations, virtual labs, remote labs, and so on, so to transfer the experience to every single student. And we have to make sure that all the test features are integrated in the appropriate way. So the instructional design is becoming a key aspect of this issue. Also, collecting specific kind of data, timing data, time on task for every single for every single student. This is also a very important aspect. So this is the outcome, I would say, a quite different outcome. These are, let's say, data from about 10,000 students. They are entering here in the first phase of inquiry. We have the high performers, the moderate performers, the low performers. You see a significant number of students are low performers. And while they are in the process, while they are performing the lesson, the system is able to interact and try to improve their skills, to fight against their misconceptions, to help them understand the problem, to help them organize their hypotheses, their models. So you see that it's a dynamic system. It's not a tree structure anymore. It's a dynamic system. High performers can move to a different level at any time because they were not capable, for example, to make the correct hypothesis, even if the system was supporting the process. Okay? And you see that at the end, if I have 10,000 students, about 5,000 are reaching the end of the lesson. Why? Why only 5,000 are reaching the end of the lesson? Because there is no time. In the 45 minutes time frame, it's not possible for a low performer to cope with all his or her misconceptions, to provide all the necessary support. So we are speaking for a lesson that is taking place at different speeds. Okay? But the educational objectives of the lesson are also dynamic. So for a low performer, I'm satisfied if he or she manages to go to the analysis phase, or even if he can finalize the experiment. So I have to be ready that I cannot design a lesson for all. I have to design a lesson where the educational objectives are meeting the needs of the specific student. This is for Greek students. It could be quite familiar. It's the very first lesson they have, it's one of the very first lessons in the first class of gymnasium when they are, let's say, entering the high school. So it's the pendulum that it is designed to be used as a time measuring device. And we have to discuss about the accuracy, about the average values, and so on. So here we have a major misconception that about 53% of the students believe that the period is affected from the mass of the pendulum. So this is our starting point in this case. And we are starting with these kind of questions. So I would like to measure the period of the pendulum. Okay? This is the task. How I'm able to make the most accurate measurement. It's giving 3 options, A, B, and C. One swing, I'm measuring the time. 10 swings, I'm measuring the time of every single swing, and I'm taking the average. 10 swings, I'm measuring the total time, and divide by 10. Why? About 2 weeks ago, there was the swimming championship, the European Swimming Championship. Now with advanced measuring system, if you see when the swimmers are jumping and they are starting, it's giving a time. This is 0.5, 0.6, 0.4 seconds. This is the so-called reaction time. And they are really very experienced on that because they are doing this for their whole life. That means when I have a measuring device and I want to measure the starting point of the swing or the ending point, I have to use a watch. I have to start and end. And this is about 0.4, 0.5 seconds. So if I measure an individual swing, I have 0.4, 0.5 to start, another 0.4, 0.5 to start. If I make 10 and divide by 10, I have the minimum error. So all the answers in principle seem correct. But there is one that demonstrates that there is a higher level of understanding of the concept. Okay? And here we are speaking for 14-year-old students. So these are the kind of tasks and challenges that the students have to. We have analyzed that. I will proceed further because the case here is not just to say the correct answer, but to explain also the correct answer. That's why more time is needed. Let's suppose that we have run the whole lesson, okay? And we are now at the reflection phase. As you have seen in the reflection phase, not all the students have managed to come, let's say, to this stage. Many of them stopped earlier because they were not capable. But the students who are arriving here, more or less, are reflective problem solvers. We can consider them with very high level of understanding about the concept and the problem. So in principle, at this level, they are convinced that the period, the oscillation period of the pendulum does not depend on the mass. Yes? I'm going to say now. This is what I'm going to say. So now, in this phase, we are, let's say, at about, we have spent about 40 minutes, 35 minutes of the lesson, and this task is coming to the students. They are convinced, they have made their tests, they have made all the measurements using the simulation and so on, that the period does not depend on months. So it's the moment that we have to bring and create a cognitive conflict. We have to test how deep is their understanding of the statement. And we are saying, we have the pendulum, the original one is the rope with the blue sphere in the middle, and we are adding an extra mass. If we are adding an extra mass, in principle, is not going to affect the measurement, okay? But the placement of the mass is important. The placement of the mass is important. In the first case, I'm putting this above. In the second, exactly at the same point where the original mass is, and in the other case under. So we are testing the understanding of the students here. So first we are asking them to predict, and then we have a remote lab, because here we need the real thing. The simulation is not working so well anymore. We need a real thing, and we have the opportunity to attach a can, a Coca-Cola can or a soda can or whatever, above, on the same level and below the pendulum, okay? And we are performing the experiment. And the students see that when it is above the period is changing. When the mass is at the same level with the existing mass, the period remains the same. And when it is under, is changing. So the question here is, do you believe your statement?
I think that because the period of the pendulum changes, and we have like some formulas, right? And the period of the pendulum is heavily dependent on the rope size, the rope length. So the first case, the rope length actually got smaller. The second case, it was the same, and on the third case, wait, what? Oh,
It's longer.
it was longer, yes.
Perfect. Perfect. So, in principle, the length of the pendulum is changing. So this is what we expect the reflective problem solver to see. Okay? So the students who are really dealing with that we are convinced that they are really reflective problem solvers. So these are the different paths. The high performer learning path, all what is expected to happen from the engagement phase till the reflection. Here we have the moderate performer. Here we need significant support at the different levels. We need additional activities in the first, so it's taking more time, guidance, and also when in the experiment, because our effort is really to finalize the data analysis, significant support is needed also here. And we have the low performers where we are really happy if they manage to go to the experiment, because they will need to devote significant time to understand the dependence between the different parameters. You know, here we have, for example, students who are changing the parameters at the same time. They are not have really the, I would say, the experimental experience to say that every single time I have to have a valid measurement, I have to change one parameter and keep making this loop. So these are very important. Here also we identify cases where the teacher has to enter in order to support the students and explain this better. So the teacher is not teaching for the average student in the class. The teacher has time to devote where it is needed, to the low performers, to the high performers, and so on. So in principle, the teacher is becoming an orchestrator of the learning experience. These are real data from 760 students, 13 years old, from schools all over Greece the last year. And we see these paths in between the different categories, and overall is demonstrating we had about 600 individual paths for these students. 760 students followed 600 different educational paths in this process, moving from one level to the other. The role of time of task, I mentioned that in the embedded assessment. You see here is the time that the different students, here are the high performers, the moderate and the low, the time they are spending in every phase. So you see the high performers, we will go very fast in engagement hypothesis to devote more time in experiment and reflection, while the low performing students are spending a lot of time in the first phases. This is because we are doing all that in order to train the AI agent, okay? So the AI agent needs data in order to support the students. When the AI agent is activated, here we see a similar form, but we see significantly increased times for all the participating students. So the AI agent is helping students more effectively to devote more time, more effective time, while the lesson is taking place. Let me ask you, in a 45-minute lesson, how much time do you think is really effective, is really learning time, is how we call it time on task? For how many minutes do you think in a normal classroom students are engaged in tasks? 20 minutes. 35. 35, okay. These are the data from the low performers. From the low performers. The engagement time for the low performers is 5 minutes. 5. For the low performers, there are two kinds of low performers. Students who have no interest at all, so they have from 0 to 10 minutes. They did something, they forget it, they are just clicking and so on, very common. But we have still students who are making a significant effort. For these students, it's about 25 minutes. I'm referring only here to the low performers, to the low performers. This is without the AI agent. This is with the AI agent. So here, again, there are the students who have no interest. Still, there is a small move for about 5 minutes. But the most important is that for the students who are really trying, the time on task is now 35 minutes. And in a 45 minutes lesson, 35 time on task is the ideal. Okay? So this is what the AI agent is really helping. Here is the picture from the test. And here you can see that in principle, this is the plan, how the students are moving from task to task. Activity 8 here it says they can give different answers. Activity 9, period dependence of mass, what they are going to answer, explanations, and so on. And the AI agent is coming and increasing, enriching the experience, is giving further information, further tasks to keep the students engaged. These tasks are created on the fly to support the specific low performers groups. Also, we have data that demonstrate that we have a very good separation between the high performers, the moderate performers, and the low performers. So the system is very effective to discriminate the different categories. It's not making, let's say, so many mistakes when it is trained well. Because if, let's say, a muon track is wrongly misconstructed, okay, maybe I will make a mistake and I will think that this muon is coming from this star instead of another star. But here, we are speaking for students learning. And if I make a mistake here, then I'm providing students with the wrong information, with the wrong guidance, the wrong support. So there is a complete failure of my approach as a teacher. There are data also from the activities we have run here the previous years. So my conclusions. So we have demonstrated that even with such a complex case, we are capable, with the support of AI, to assess multidimensional representation of the competence. And we can really support this strategic and self-regulatory process, which is the development of the problem-solving competence. We have identified significant differences between the same groups, between the low performers and between the high performers, related also to the difficulty of the tasks that we are offering. So this is the reality in real classrooms. The learner diversity, the varying levels of prior knowledge, the misconceptions of the students, The differences in the self-regulation are parameters that we have to take into account, which is making the traditional testing impossible to be implemented. With AI, it seems that it is possible. And finally, the time on task. As I said in the beginning, from the design, it's a very crucial parameter that demonstrates the students' engagement. When the students are engaged, I have more chances to develop the competence more effectively. So the completion of the task does not always demonstrate a clear understanding. But with AI, I'm able to see how the students are reaching these conclusions. So the same score can have different learners. It's important to see how we behave while we are solving a problem, which the final answer in a test cannot give it to us. And clearly, we can demonstrate that learning and assessment can happen in the same time. This is our, let's say, vision for the future. These are the students' paths. If the content is organized in the appropriate way, the Ministry of Education is developing now a huge database with 15,000 digital objects organized at different levels for high performers, low performers, and so on. So while the students are in the learning process, while they are working on the different tasks, content can enrich their experience coming directly from the AI agent and helping them to understand the phenomena better by providing simulations, virtual experiences, remote labs, and so on. And the next step in the future would be really to have a fully technology-enhanced system really to support the school development at the organizational readiness, at the technical readiness, staff readiness, and based on that to make a whole strategy for the whole development. And this can be done with AI. At least this is where we are working on. So the task of the teacher is to present alternative paths for the students, for all students. For students who are capable to solve problems, for students who are not capable. Still, it's important to offer them a different door, a different staircase to go higher. So I hope I have tried at least to demonstrate that this AI has some significant impact, could have some significant impact in learning and in education also. Thank you so much.
The student is not even extrinsically motivated to care about the exam. Many students who take PISA just do not care. Their results do not affect their own grade in a physics teacher grading. The results that they will get will not matter for their university entrance, so they just click randomly. You may even check that, like, there is no time, they give an answer before there is enough time for them to read the question itself. They just do not care about the exam. Not only that, like the students, I guess most of them are selected, like who will take even in Greece and even in our country, are randomly selected who will take this examination. They do not get any financial compensation for that. For psychology experiments, like you can sign up and you even get some kind of financial compensation at the end of the psychology experiment to participate in it. Here, you have the students, the grades, the results they get from the PISA examination, finding is that in the lower performance, you have dumped all the students who just do not care. It's not that they are low performance. I don't care about, let's say, physics. Like I'm in arts. And I want to do, and I will just click randomly on the exam.
Yeah. The process that I have presented in principle demonstrates how we can transfer a PISA-like experience to the real school classroom. So we are transferring the PISA process in the real lesson. So instead of having to develop a digital aquarium or solving a problem with mobile phones and so on, which is out of context, we are transferring this process, exactly the same process, in a traditional lesson, like using the pendulum or the photoelectric effect and so on. So we are getting the results from this.
I definitely oppose, sorry
Yes,
to interrupt you.
and the results show that for the low performers, the data are quite similar. So even if we transfer this experience, I'm referring always to the problem-solving competence, okay? Not to science, PISA science test. If we do that in the normal classroom, in the tests we have done in Greece, the rate of the low performers is the same. It's about 40%. And as I have presented here, there are two different profiles of the low performers. Exactly the number that you said that they don't care, they are not motivated. You see their engagement time is 10 minutes maximum for 45 minutes lesson. But we have still a significant amount, more than 50% of them, so about 20% of the total sample, who are really trying to improve. So if we manage to deliver for them, for these 20% of the students, it's still a very valuable issue, okay? I don't have a magic stick to engage the rest of the 20% that they don't care. They will be always there. Or we have to find other innovative ways to engage them, okay? But we will always have students who will click, 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 and end the experiment in a few minutes. Okay?
Sorry? Yeah. How do you measure the engagement time in minutes? I know particularly, like the teachers who instructed, okay, the student will sit till the end of the exam, like must sit till the end of the exam. Like they do not have a choice to, like, let's say, I'm done and I leave from here. And even then, the student like will read the question, will just wait to give the answer, but nothing.
In fact, the system, the environment is designed exactly like this. The whole experiment is designed like this. So it's measuring the engagement time from challenge to challenge. So there are about 20 different challenges. So in principle, the students have to deliver one after the other. So you can measure really the engagement time. For every challenge, we have the optimum time. For example, to solve this issue with the remote lab, it needs minimum 5 minutes. So if you have many students who are spending more time at this level, at the reflection phase, maybe something that we can accept. But when we have the case like the first question, where we are allocating 4 minutes, if we have students who are spending 8 minutes, 10 minutes to that, then this is rejected from the sample, okay? Because this means that this student has stopped. Is not interacting with the system anymore. So the system is measuring the engagement time for every single student. So I'm able at any time to see how many students are engaged and how many students have stopped, or how many students have just make all the clicks in the first 2 or 3 minutes, and they have finalized the test. So the engagement time is measured from the system.
The quantity
Yes, yes.
the quality is still not measured.
We can continue the discussion in the break. Okay?
Thank you.
In the break, sir. In the break, we must continue.
Okay. Thank you.
We thank Mr. Sophocles for the well-documented presentation, which gave us a comprehensive understanding of the topic. Now, we will continue with Argyris Koumtsis, a Greek physicist, an astrophysicist from young age. She showed his interest for physics and mathematics. He participated, winning, of course, to many national competitions. In 2016, he attended a program at MIT, and at 2017, he was selected for a research internship at the University of Oxford, among hundreds of applicants. After completing his study at Aristotle University, he continued his academic career in astrophysics and pursued a doctoral research in solar space physics in the Max Planck Institute and the University of Göttingen in Germany. His academic journey is an inspiring example of determination, scientific excellence, and equal access to education. Your stage is yours.
Okay. How can I change the slides?
Enter.
Where is the, here, okay. And where is the enter?
There.
This one.
Yes.
Okay, perfect. Okay, it may be something. Okay, thank you for the nice introduction. I'm very happy to be here. Wait, I'm going to leave my stick. Okay, so I have many difficult things to tell you. I have many interesting questions for you. I didn't make pretty slides because I wanted you to more concentrate on what I'm saying and not so much to what I'm showing. So try to do that, and this way you will also have an experience a little bit more similar to how is my experience when I am following a talk. I also want you to not be shy, so at any moment, if you have a question, maybe I'm using a word you are not familiar with, maybe some concept is too difficult. I haven't given a talk to high school students for a long time, so it's a little bit difficult to bring the level from the university to the high school. Anyway, whenever you have a question, you raise your hand. It's extra important for me because I cannot see your eyes, I cannot see if you're concentrated, I cannot see if you're following me. So it's very important to have some interaction. You ask me questions, okay? And my teacher here will give you the speech. Okay, let's go. So I'm a physicist. I will talk to you about how we can use machine learning in physics. I heard you had a very nice talk from my professor, Nicolas Terioulas, yesterday. So I'm sure he made a very good introduction. Before we talk about machine learning, I will sneak a little bit of physics into the talk, because that's always good to do. So let's talk about the sun. We like the sun is very nice. I want a volunteer to describe to me what you see here on this picture. I hope I changed the slide, by the way.
Yes, sir. Just a minute to give the mic.
And always say your name, please.
Say your name first.
Hello, my name is Omiros, and I see a picture of the sun with some solar flares, certainly, especially to the left. of the sun in the picture, and I also see some solar spots, especially on the upper central part of the sun, and
Okay, that's fine, Thank you. Perfect. Okay, so when we look at the sun, ideally, don't look to the sun with your eyes, okay? I'm speaking from experience, not good for your eyes. What we see is the solar spots. So, do you know what are the solar spots? Since you used the word, do you know what they are? I don't want a formal definition.
yes, could you please repeat the question, because there was a...
Could you...
solar spots are basically in areas of the sun where the temperature is lower than the areas behind it. So this creates the effect of it being seen to us as black or dark in general. And these basically have like a cycle in which...
Okay, that's fine, perfect. So we see the solar spots, they are a bit darker because they have lower temperature. Things that are warmer, they look brighter. Things that are not so warm, they look a bit darker. Okay. So solar spots are generally within the areas of the suns that we call active regions. And the reason why we call them active is because this is where we have solar flares. Okay. What are solar flares is the next question. Solar flares are violent events. They're big explosions that happen in the sun, and they throw randomly to the space a big amount of radiation, a big amount of energy, and sometimes they even throw very hot plasma, very hot mass. And you probably understand from this description that if the solar flares would hit the Earth, this would not be fun. They're happening every day, sometimes more, sometimes less. But we are lucky that they don't hit the Earth very often, or when they do, they're not that strong. To give you a feeling for how bad this is, in 1830 or something, they hit the Earth and they burned the cables for the telegraph. Probably you don't know how thick are those cables, but are super thick. And at that point, our civilization was not depending that much to electronics. Now, if they hit now the Earth, we will have serious problems because all our telecommunications, our satellites, the machines in the hospitals, every electronic thing would be very much affected. So, as a humanity, we would like to have a way to be able to predict this phenomena. So I would like to have an instrument. I go every day in the morning. I look at it and it tells me, okay, tomorrow there is a solar flare coming. Do whatever you want to do. If it's very bad, you have to hide in some cave. If it's not that bad, just switch off your satellites. This is a very difficult problem in solar physics, one of the most important open problems in solar physics. By the way, solar physics has nothing to do with solar panels. Solar physics is the study of the sun. So it's basically astrophysics. I'm saying this because many people when I tell them that I studied solar physics, they ask me if I know things about solar panels. Okay, so we want to have a way to predict solar flares. Some of the best models that we have, are the machine learning models. And this is why I did this introduction, because I want to talk to you a little bit about these models. But before we go there, I want to ask someone to explain to me with simple words, what is a physics simulation? Like, if your grandmother would come to you and ask, explain to me, my child, what is a physics simulation? And let's assume your grandmother is not a physics professor, okay? So how would you explain it?
It's like a laboratory. My name is Faris. It's a laboratory where we can test things that could happen in the real world without without actually having to buy resources.
Okay. The other answer?
The third one.
Okay, let's go.
So a physics simulation, Lucas. So a physics simulation is when we want to study something under controlled conditions. So we use a laboratory or something similar to have controlled conditions and study it more carefully rather than just waiting for it to happen on the natural habitat.
Okay, perfect. Okay, let's go.
The microphone.
My name is Elena, and I'd say that it's basically a simulation where we test whatever we're interested in, and sometimes it can also be digital.
Okay. Let me combine now your definitions and give you my own definition. So I would describe as a physics simulation that is a computer experiment where we write a computer program to approximate a natural phenomenon. Wait, sorry, I have a call. Okay, so the question is, how do we do this? Like, how do I take this phenomena from nature and tell the computer how to approximate it? So most of the times, there are different ways to do this, okay? But most of the times, what we are doing is that we are solving with our code, with our computer program, we're solving differential equations. A new difficult word. What are differential equations now? You know the normal equations, right? Like x squared. Sir.
Differential equations are basically, you have an equation and you have like the derivative, and you need to solve when you have the derivative.
This is true. This is true. It's interesting that you know what the derivatives are already. Okay, that's nice. So what I wanted to say, you know the normal equations, right? You know I have x squared minus 5x plus 6 equals 0. And when you solve this equation, what do you get? You get what value of x is satisfying this equality, right? Okay. Differential equations are equations that their result, when you solve them, they give you as a result not a value, but a function. So, for example, when I solve the differential equations of motion for the stars and the planets, what I get as a result is how a planet will move or how a star will move. Okay, so I make a program, I write a program in the computer, I give it some parameters, and then it is solving these equations for me, and it gives me, let's say, the function or the graph for how something will evolve in time, or what is the structure of some particular event or phenomenon. Okay. This is the traditional way that for like many decades now, physicists, computational physicists, do simulations. These very standard procedures. There have been many articles, many books. It's really a whole science. The advantage there is, as someone said before, I don't remember who said it, but as someone said before, I don't need to wait for the phenomenon to happen to measure things, but I can do it in my computer and I can measure everything that I want there. Okay. Now, the problem is that to do these simulations, we need to know the values of some parameters so that we can start the simulation and have it evolve and to watch it. The problem is that for the case of the sun, We don't know these parameters. We cannot measure them, and we cannot infer them. It's not like in other domains of physics, in other fields of physics, that you can put, I don't know, let's say you have a material, you go to the lab, you put it in your microscope, and you measure everything you need, and you make your theory. In astrophysics, sometimes this is not possible, because it's not that I can go to an aeroplane, take a sensor, get it out of the window, and measure how much is the temperature on the sun. There are ways that we can indirectly do this, but unfortunately, we cannot see inside of the sun. We can see up to the surface, we can maybe see up to the atmosphere, but we cannot see inside. And because the solar flares have to do with processes that happen inside the sun first, and then outside of the sun, this is what makes them very difficult to predict with traditional computer simulations. And this is where the machine learning comes. So, now, I'm sure yesterday Mr. Sterioulas explained some basic things to you, but I want to repeat them because I think this doesn't really hurt. I lost enter. Where is the enter? I want to go to the next slide.
Here.
This one, okay. Okay. So what do we see here? Who is going to tell me what do we see here? No one.
My name is Aya, and we see a linear graph with all of our tested situations, and we have an approximate best fit linear graph.
Perfect. Okay. Could you imagine a very, very easy physics experiment from junior high school that would give us this kind of points? Forget about the sun now, forget about astrophysics, we will go back there. But I want something very, very easy, like something trivial that you learned your first physics lessons.
I remember one, I think with like the coil we did in middle school, where we put like a mass on the coil and we see how it's retracted.
Perfect. This is exactly what I had in mind. So how is this law called? Do you remember?
Not really. I think something from F, starting with F.
Okay, it's fine, it's fine. It's not so important to, it's Hooke's law. It's not so important to have more answers on this. Okay, so what is Hooke's law? I have a spring. I displace it a little bit, right? And the force is rising linearly in proportion to the displacement of the spring. In real life, it's not a straight line. If I take different measurements, now I think we have like around 10 points, whatever. It's not a straight line because springs are not perfect objects. Okay. Could someone, no, let's keep it for later. Okay. So then the question is, if I want to find the constant of the spring, this K, that basically, okay, maybe this is something for you. What does it show me? Like, what is this constant of the spring? What does it show me for a spring? If it's high or if it's low, what does it show me? Someone can answer.
My answer might be dumb, but I think it's the like natural length of the coil when we don't have a mass on it, like how it stays.
So if the spring has a length of 5, you say that this constant has to be 5, for example.
constant K of a spring says how hard it is to stretch it in a way.
Okay, perfect. That's good enough. Okay, that's good enough. So, what I want to convince you about is that when I plot these points, I take different measurements, I take the spring, I displace it, I take these measurements, the slope of this graph is this constant K, and when it is higher, the spring is harder to stretch. Okay, so now I tell you that this line that I plotted here is the best line that is passing through these points. So it's the real constant of this spring. The question is, do you believe me? Like, why is this the best line and is not another line the best line? This is the question. And how do we define which is the best line? This, what I want to explain to you now is...
We have someone to make a remark. Okay?
Okay.
Give the mic.
My name is David. Well, we find the best line by adding the distances from points on one side of the line and on the other side, and we try to find them to be equal.
Yes, this is correct. So there are different ways to do this. But the most standard way, and what I'm telling you now is half of machine learning. You understand this? You understand half of machine learning, okay? So what we want to do is we want to define an objective, we want to define the goal, and we want to find the line that is satisfying this goal. So the most frequent goal is that we take the distance of each point to the line, we add all these distances together, and we want this sum to be as small as possible. And we change the line around, let's say we change the line around, and we find the line that is satisfying this condition. So the total of the differences between every point and the line is the minimum. This is what we call in machine learning regression. So what do we try to do? We try to find a function, a line, a plot, that is describing as best as possible the phenomena that we are studying. In this case, it could be Hooke's law. It could also be the linear motion of an object. It could be any linear relationship. It can also be any curvilinear relationship. It doesn't need to be a line. You can imagine a curve. We still try to find the curve that is passing by the points the best way. But be careful. We don't want the line to pass by on top of the points. We want to have the one that is the best when we look at all the points together. Okay. This is really half of machine learning. The way to do it is not so relevant now. This you will learn if you go to the university. You will learn this. It's not even that difficult anyway. It's not my job to explain to you now. So now, who is going to tell me what we see here on this picture?
Okay, so we have split the points into two groups, the blue one and the red one, with the blue ones being the ones whose value is lower than 6, let's say 5.5 pretty much, and red being the ones, their x value, I mean, and the red ones are the ones whose x value is higher than that. However, we have also set some of the points as unclassified, and these are either the ones that are on the line that we have already put as like the middle, as well as points that had higher deviations than most.
Okay, perfect. That's a perfect description, thank you. Now, I want you to tell me what could this picture represent physically? Like, what experiment could I have done to get this picture? Let's stick with the springs again, because it's a nice example. Okay.
It could have something to do with pressure maybe, and how deep is it?
Say again?
It could have something to do with pressure and how deep we're measuring.
Could you maybe think along the lines of the spring again? That we have like a spring, a coil.
How big the constant is?
But if the constant was big, then the points should still be along the same line, right? Along the same straight line. Why do we now have two regions?
You need water?
Oh, maybe.
Just grab it.
Thank you.
Nothing more.
No, that's fine. I can keep it. Do we have someone, or should I? Ah, okay. I'm sorry for the person who is carrying the microphone around.
Okay.
Okay, my name is Dimitris, and could this be about the mass that extends the spring?
You're going to the correct direction. What I wanted to say is that maybe we have two springs, right? Because these two lines have different slope, this could tell us that we have two different springs with two different constants. And what about the points that are nowhere? This could be, for example, that we did an experiment 50 years later, and the spring was a little bit rusty. So when it becomes rusty, again the constant is changing. Or it could be that we have a completely new spring, a third one, or a fourth one, or whatever. Okay. This is not so important. I just wanted to show you that we can also use machine learning not only to guess the value of a point, like we did before, like to guess a function or to guess a plot, but to also try to group points into different groups. And by this grouping, to try to guess their properties by associating them with this group, by classifying, as we say. Okay. This will be even more useful later. Okay. Who is going to tell me what we see in this picture?
Okay, so we see three different ways that you can make a line of average positions. For example, the first one is similar to the one we saw on the previous graph. However, here the points are in completely different, distributed in a completely different way. Thus, this is why it is deemed as underfitted. On the second graph, we have a line that is more or less following the average position of these points. And on the third one, we see a line that connects nearly all of the points. And this is why it is considered as overfitted, because it is no longer accurate.
Okay, exactly. So what's the question here? The question is, why the middle graph, why is the middle graph better than the other two? I guess for the first one, you can kind of feel it, right? Because you say, okay, I want to approximate this phenomena, but my line is not passing very well through the point. So it's maybe not the best line. Okay. But what is the problem with the third line, is the question. Like, why is the third not the best and the second is better? This is a very difficult question, so I will be very happy if you manage to answer.
Because it passes through all the points, so we can't be sure which one is the right one.
But why is it a bad thing that is passing through all the points? Doesn't this mean that if it's passing through all the points, it describes the underlying phenomenon better?
I'm giving the microphone to another student.
I am Telemachos, and I think that it depends on the value.
On what do you mean it depends? Like, elaborate a little bit, if you can.
Can you repeat the...
Yes. So the question is, you see that the third line on the right is passing by the points, right?
Yes.
Why can this be a bad thing? Because you could think that, okay, I have a line, I have a point, the line is describing the phenomenon. Why I'm not happy?
It's a bad thing. I believe that it depends on the value. But if the value is big, it may be a very good thing.
Okay. That's also going again.
To another student because I can see many hands.
Okay.
Because in this graph we take into consideration points which are with a really big error, and they might be not a part of the tendency that we follow.
Perfect. Thank you. That's a very good answer. That's a very good answer. So this is one reason that if you have a single point that is an outlier, as we call it, that is very far away from the other points, that is a mistake, like in real world, things happen. Like you make an experiment, you can forget the lab of the door of the lab open, and this could destroy the results, for example, right? It can, like random things happen. If you have a single bad point, when the line is passing by all the points, if you force the line to pass by all the points, then the line is not describing very well the behavior of the system. Is very much skewed, is very much destroyed by this accidental single point. Or if you have big oscillations on your data, then it could be that if you want to guess the value between the points, then it's, again, not a good approximation. Okay, so now I want to go back to the solar physics, now that we're understanding a little bit more of the foundations. So, from what we said already, first I have to say something else, okay. So, the first exercise that we did, the Hooke's law with the line passing by the points, is what we call regression, okay? The second exercise, the previous picture, that I told you that we can have two springs, is what we generally call classification. When we try to group the points into different groups. So, for example, there it could be two different springs. We see the group of points, the one group. We see the other group. We say, okay, this is the one spring, this is the other spring. Okay. These are two different things we can do with machine learning. So we can use the data to learn the pattern and guess a function or a graph. And we can also use the data to guess different categories, different phenomena that exist within our data, within our environment, within our laboratory, whatever. Okay. Now, when we try to predict when a solar flare will come, we can use different approaches. Okay. For example, I can look at active region, I can look at it, I can take a picture of it. I can take actually many pictures of many active regions, and I can see how does this picture look like, and did I get a flare, a solar flare, connected to this picture? And I make a very big collection of this. So on the one hand, I have the picture. On the other hand, I know if this picture gave me a solar flare. And then I can make two groups. One group that gave me a solar flare, another group that didn't give me a solar flare. And now you may be asked, why does this work? Why doesn't it work when we do the traditional computer simulation and this could work? The answer is that we don't know and we don't understand the patterns that exist within the data. But when we take thousands or millions of pictures, the algorithms, the different machine learning algorithms that we can use for this job, they detect these patterns automatically. And they separate these images into these groups. Now, this is the very basic idea. There are like hundreds, thousands of papers that use very many variations of this. For example, what you can do is you can also use not the classification. Classification is what I just said, right? Like to just separate the active regions, the pictures, into two different groups. You can also use the regression, what we did with the springs, to try to guess when the next flare will come. Of course, it's not a single straight line, as it is with the spring. It's much more complicated. It's many more dimensions. But at the heart of it, the basic idea is the same. You gather data, and you try to find what is the best line, what is the best. It's maybe not even a line if you go to many dimensions, but what is the best approximation that can satisfy at the same time, as best as possible, all the points that you have. And then when you have this line, you can guess what will happen in the future. Does it work perfectly? No. Does it work better than the other method that we have? Yes. What is the time? How much more time do I have? 10 minutes. Okay. Okay, you see, I'm a physicist, so I talk a lot about physics. So I passed more of the time talking about physics and a little, not so much about finance. Can you imagine? No, let's take it in a different way. So these algorithms that we just talk a little bit about can also be used in finance. And this is why many banks, insurances, hedge funds, the big players, are employing physicists, and mostly physicists with PhDs. From the second semester of our studies, if you go to study physics, I hope you do because physics is a wonderful thing to study, you learn this linear fit. We don't call it regression, we don't call it machine learning, we just call it linear fit. And this is what you will basically do for many semesters when you have a physics lab, because you take the measurements, you make this, you plot these lines, and you try to find the properties of the thing you're studying. And because of that and this experience that you have, many physicists get jobs in finance. Could someone imagine what application these algorithms could have in finance? Both the regression, like to guess the values of the points, and the classification, to guess what is the category of some point, of some event, of some phenomenon.
My name is Petros, and I think they could be used to predict the price of stocks depending to world events or other prices of stocks.
Exactly. This, fortunately or unfortunately, is the most used use case of machine learning in finance. You have the stock markets, you have stocks, you want to make money fast, you want to buy low, you want to sell high. Machine learning can help you to find these patterns. They're very complex patterns, by the way, because everybody's trying to do the same job. Also, another application is how banks decide to give loans. So you're a big company or you're a person who wants to buy a house, you go to the bank, you give them your details, your income, how much money you have, and other things that they're asking you, and they try with the machine learning algorithms to see if you're going to pay back the loan or if you're not going to pay back the loan. Now, I'm not working on this. This is not my job at the moment. I just wanted to talk about like many general use cases. So if you, let's say we're all going to become rich, okay? I guess we're all going to become rich anyway. And if you become physicists, you will be poor anyway. So if you want to become rich, the time is now before you become physicists. So I have a good idea. We go, we buy flour, we buy sugar. We make lukumades. How do you translate it in English? Donuts, maybe. We go to Chalkidiki and we sell them. We don't give receipts, so this is all illegal. And it's a profitable business, believe me. Let's say we make $1 million during the summer. Now, we have this illegal money, right? The problem is, how do we make this money legit? How we legitimize, as we say, this money? We have to pass them through the financial system. And because people do this, and they try to do this, there are some people, in the banks mainly, like me, that we use machine learning algorithms, the same algorithms that we use to classify the solar flares. We use the same algorithms to find the bad people like us that will have illegal funds, illegal money, and they try to move them within the financial system, from bank to bank, from the bank to insurance, and so on and so forth. Okay, now, I want to give you some more examples. So, let's say that there is, what is suspicious? What is suspicious as a transaction, right? So, if I have a bakery, and I suddenly get 1 million, like we all go to the bakery after we sell our donuts in Chalkidiki. We'll all go to the bakery and we're like, okay, we have our $1 million, we will give it to you in cash, and you make a transfer to us in the bank. And suddenly, the baker has 1 million euros to his account. This is weird, right? Like, it doesn't happen every day, at least to the bakers that I know. So, if we suddenly see in our models such a big outlier, such a big discrepancy to the average, this is a bell. So our algorithms are trained to find these anomalies. Now, if suddenly everybody is sending money to me, because I had the idea with the donuts, we all made the money, and I'm like, okay, guys, I want 10% from everybody because I had the idea. So everybody's suddenly sending money to me. This is also weird. So our algorithms are also trained, we teach them to also classify this, again, as suspicious behavior. But there are other patterns that we cannot explain. We don't know why these patterns exist within the data. We cannot guess. Like, this, what I tell you, is things that we see in practice, and then we can understand and implement. But there are other things that we don't know why they exist, but they are associated. Like when we send these cases to the police, let's say, to the people who investigate these transactions, then they check them and they tell us, okay, this was a criminal. We don't understand why this behavior is suspicious, but the algorithms have the ability to use all the data that we have and identify these patterns and tell us that this is suspicious behavior. So we can use machine learning to protect ourselves from solar flares. We can use machine learning in finance to give loans to people. We can use it to become rich. By the way, don't do this. You will lose your money. These systems are very sophisticated. Don't listen to people in YouTube that tell you use machine learning to become rich in the stock market. And we can also use machine learning to find the people that became rich within illegal ways and get them to jail. Okay, that's it from me. If you have more questions, let me know. Thanks for your attention.
Can machine learning break encryption?
Sorry? I didn't understand.
Can machine learning break encryption?
To break encryption. This is what you said, right?
Yeah.
I'm not an expert in cybersecurity and encryption and these kind of things. So I will say formally that I don't know. I could imagine that people are using more sophisticated, like hackers are using other, not so much to break encryption, but more to guess passwords. This is what I know. But it's really not my expertise. But what can break encryption is quantum computing for sure. This has nothing to do with it, but like, this will be the problem with quantum computing at some point, that it will be able to pass by brute force to decrypt basically all the passwords.
Thank you very much.
You're welcome. Okay, thank you very much.
Me? Τώρα. Γιατί δεν φεύγει? Θα φύγεις.
Ναι, πατάμε το... Όχι, δεν χώνεσαι. Φωνάζουμε.
Όχι, θα φωνάξω εγώ. Άνοιξε την εσύ.
Ποια?
Την ομιλία του.
Αυτή πρέπει να είναι. Ναι.
Βάλτε το λίγο να είναι στο κεντρικό.
Okay.
Και θα μιλήσω εγώ. We'll continue the session. In a few minutes, we'll speak Professor Sener Oktik, a distinguished scientist a dear friend. Professor Şener Oktek is a Turkish physicist, researcher, academic specializing in applied physics, material science, and photovoltaic technologies. He graduated in physics from Ankara University. He has master engineering. He completed his PhD in applied physics and electronics at Durham University in the United Kingdom. He has an astonishing career. Many scientists will jealous it. Throughout his career, he has worked at universities and research institutions in the UK, Italy, Germany, and Turkey. He also served as a rector of Muğla University from 2002 to 2010. His research has focused particularly on solar energy, photovoltaic cells, semiconductor materials, and renewable energy technology. But Professor Oktek has a very great career, an important career in industries. He was president of Research and Technological Development of Seisenkam Group from 2012 to 2020 and has worked with organizations such as BP, Solar, and Imperial Chemical Industries. He has published more than 100 scientific and technical papers. It's one inventor or co-inventor of international patterns related to photovoltaic technology. His career is an example of how scientific research, renewable energy, and technological innovation can work together to address global energy challenges. It is an honor me to present you Professor Senik. Your stage is yours.
Should I say good morning or good afternoon? I'm Şener Oktek. It was presented my CV. Thank you very much. I've been in academia and industry for almost 50 years now. Over those years, one thing I did not understand, why the students stay at the back seats? Why the front seats are empty? I checked with AI. It says they might be hiding behind. They said they don't want to be exposed to others or to the front seats. Sometimes they are as a group sitting and talking with each other. They have conversation to sort out. They have several reasons, but one thing psychologists said, actually, engagement is not very much related where they sit. And as Sophocles explained, engagement is something else. It doesn't matter where you sit, but the communications become easier if you are really at front seats. Okay, today's task given to me really explain the AI and what is the effect of AI on the major task you have in your life, which is acquiring knowledge. Let's start from the birth and acquiring some skills. Again, it starts from the birth. You start walking, start talking, start discussing. And of course, joining them dynamically have some competencies. If you walk fast, you become a runner. If you talk fast, you can become a speaker, etc. So these three pillars in your life are very important. Knowledge, skill, and competencies. That's why you have your qualification given to you in the secondary schools, in the universities, even in your job. Your knowledge, your skills, your competences. Okay. This has been changing over the years. over the years, in my lifetime, there are tools improved or augmented me acquiring knowledge. And there are tools really improved my skills. And I felt more confident to do something because of those tools. Now we have the era, which is now it's called artificial intelligence. Okay, sometimes I think this is not a correct definition. Because when you say intelligence, intelligence needs conscience. I don't see any computer or any software or any agent have some conscience. So probably the definition of artificial intelligence needs to be open to discussion. It could be being more clever. We can call artificial cleverness. System is much more clever than you, but doesn't have a conscience. So today, I'll go through what happened in these two words and explaining to you in general terms. I know some of you were very much involved with this concept, but I'll go through historically as well. This is the things. When you say knowledge, what do you know? Skills, what you can do, and the competences, how you can combine them. That's your qualification. But you are in the secondary school students. You all learn this simple equation of really how the lever works. You've got fulcrum, load arms, and you've got effort arms. And there's a case in somewhere in the world, they are trying to get out a car from water. They order a lift, and they brought the lift in here, and they try to get it out. Of course, everybody's watching it and say, okay, how's it going to happen? And they always think of this equation or not. Or the driver doesn't know anything about that, and he starts doing the job. This clever guy, get this one out. Your engineering mindset, I can do it. But after a certain point, that balance is changing. And you can see, actually, the actual lift goes down as well. So they think, okay, we are engineer. We know the equation, force arm, load arm. We have to bring larger one. They bring a larger lorry with a larger lift. They start operating. And of course, it was easy to take the white car out, but there was a lift inside, and they tried to do it that. And it was going quite well until the balance changed, and they dropped. Okay, you shouldn't be really amazed. Okay, the actual monkey has a less intelligence according to our understanding. Might say, whoa, what's happening? But you shouldn't say that because you know the equation, you have the knowledge, you have to be skilled to apply it. And what do you think AI thinks about it? How we can apply AI in here to explain in that. So at that stage, we should stop and think, what do we mean by artificial intelligence? Is it a kind of computational system that can perform tasks traditionally we do it? Processing vast amount of data, using advanced algorithm, which has been experiencing with different use cases, and competing. Actually, we start actually thinking of what is AI? When we say AI, it's a quite nice word. Let's have a look. How the knowledge we say, okay, what do you do? But in the age of AI, information is everywhere. And AI can find instantly whatever you want. And skills, what you can do, as we described. And in AI, automates many things, and you think, oh, okay, my skill is improved in this age. And when you lack competences, as I described before, competences is how you can combine your knowledge and your skills effectively to apply real-life cases. But when you have AI, what you do, need to solve complex problem much more easier. You think that our competences has improved. It is. It is. The outcome is your qualification. Okay. When we say AI, I know you are in it, but how do we know really how far we have to go, the concept of AI? If you go 1950s, some years ago, you must have known the Turing test. One of the guy asked a question in codes. That was the first idea of sorting codes during the war. This guy called Alan Turing say the machine can think. That's what it started. This AI idea goes back to 1950s like. Then in 1956, the AI concept as a concept born in the Dortmund conference, in the summer project application, etc. There was a John McCarthy really start using the word of artificial intelligence. I don't know how correct that concept to me, but it has been used and still we are using it as artificial intelligence. There was some period which is called AI winter. In 1970s, people lost interest in AI. So learning machine by algorithms, etc., was dead. Then in 1980s, there was an era of expert in AI. There are knowledge-based systems become commercially successful. I really asked your attention to the word commercially successful. If anything is not commercially successful, academically we can go nowhere. Should be commercially successful. You should be able to earn money out of it. In 1980s, there was an expert system used in industry. And AI is applied medicine, finance, manufacturing, and engineering. And simple reasoning really defined the AI. So buzzword is commercially valuable. Doesn't matter in health, finance, whatever. Then, in 2010s, there was a period called deep learning revolution. Availability of big data, powerful GPUs, and improved neural network. Some of you might think that neural network as a concept come with AI. Before that concept of AI much more fashionable, we used to use neural networks. One of my experience, as it was explained, my life really goes between university and industry. I was working for a biggest glass company of Turkey as a head of research, and we were trying to improve one chemical process. It was so complex. This is producing soda ash from salt. So to improve the actual process 1% makes hell of a lot of money. So we used neural network something like 15 years ago to improve the process to do the actual reaction with the less energy. So the idea of neural network is there. That's why deep learning revolution, it became quite going up in 1910s. In 1960s, there was a kind of, probably most of you know that AlphaGo defeats the Lee school. There was a fight between different concepts. And of course, after 2020, the era of generative AI. This is the emergence of foundation models. It was mentioned large language models, LLMs. There is widespread adoption of now everybody is using ChatGPT, Gemini, Cloud, Lilam, etc., etc. The rapid advances has happened in autonomous AI agents, AI-assisted software development, scientific discoveries, education and healthcare, there was a rapid advances using AI in this field. And there are emphasis now on AI ethics. This is quite a big problem with AI. And trustworthy of AI, responsible AI governance. How we govern the AI? In the future, some countries might advance in AI to the level dominates all the world. And how you can really deal with it, how you can compete with it. There's a big problem with governance of AI over the years. In your time when you are in the work, you will see, I cannot do it because the actual AI agent belongs to Germany, United States, and you couldn't go further, stuck there, like in nuclear energy, for instance. So what we need probably in the near future, some kind of international AI commission to govern the AI. Okay, and of course, AI safety and regulations are quite important. In that stage, I mentioned one thing, which is quite important for the AI era. It's a Nobel Prize in 2024. This was given to Professor Geoffrey Hinton from University of Toronto, Canada, and John Hopfield, Princeton University of USA. In here, the guy, Geoffrey Hinton, I should spend a couple of minutes to talk on him. He is really referred as a godfather of AI. This guy was really developed when pioneer neural network using artificial intelligence, etc. Then he really introduced the face recognition, pattern recognition, etc. Of course, the big company like Google, in the Google Brain project, he employed him. He worked there for a long time. The development, he got frightened. He said, where is it going to? He started really become edgy on the possibilities with AI. He left in 2023. And now he's going around really talking on possible danger of AI for the future in any field. If you're interested in, really, you can go this website under there, watch one of his talks. It's quite interesting. And of course, his concerns were regarding AI-generated misinformation and deep fakes. Okay? You might be graduated in any area or a secondary school with a misinformation given to you, and you start believing, and then you might have some diploma which could be fakes. This is happening in the world. And other concern, loss of human control over the increasingly capable of AI system. When we are going to lose the control of AI? And of course, the weapons. Autonomous weapons was one of his main concerns. Because of the wars, we're already living really now. You got the drones and sending everywhere. You don't take any risk, more or less, really. Just a couple of millions, you can send many drones to somewhere, hit it, etc. This is quite difficult. Of course, the job displacement, it was a subject before, and the need for strong AI governance. It was his concern. In his talk, he really mentioned how it should be. Okay, the other guy, he's a chemist, but they use really artificial neural network, the ANs. He uses deep learning, optimization, algorithm, machine learning in chemistry. Okay, where are we going to? Let's look ahead. Artificial general intelligence, AGI research, human AI collaboration, that's what we need. Robotics and embodied intelligence, personalized education and healthcare, sustainable and energy-efficient AI, international AI governance and regulation. These are the fields we have to concentrate nationally and internationally to improve the actual impact of AI to us. When we look at the capabilities, when you ask ChatGPT, that's what you get. He says, okay, core cognitive capabilities of AI, we keep discussing, this is perception, learning, memory, reasoning, planning, decision-making, language understanding, generalization, adaptation. These are the things of core capabilities of AI. And what are the main pillars in AI? It's the data, hardware, and algorithms. In the first day, it was given 5 minutes to me to introduce something. I said, okay, AI is digital, but you are not digital. You are analog. So you have to take this advantage of being analog. We'll be discussing really what kind of advantages it gives to you. Without the data, which is collected digitally, and which should be transferred to digital environment to be used by AI, and AI needs hardware to use it, and of course, that's what you come in, but it is taken by AI soon, the algorithms. You know, this gentleman yesterday giving the speech, he says, he is not writing the codes anymore. People not start really thinking of algorithms. I ask, can you write an algorithms for me for this purpose? So this is the major pillar of AI. When you look at the journey, we can really describe 5 different levels. One is the beginning 1950s and the 60s. Level 1 is rules and expert system 70s, 90s. And level 2, machine learning emerges in 2000s. Now we're all very much excited in machine learning, trying to sort everything, explain everything with machine learning. Level 3 is a deep learning revolution. It starts from 1910s. And of course, AI in real life at scale, 2020. Now we are at the stage, we are feeling AI, whatever we do. And of course, towards intelligent partner. When AI is going to come, be an intelligent partner to us. Okay? It is growing fast. We all feel. Why it's growing fast? The first one is explosion of data. Explosion of data. When I say data, you need to collect the data, but you have to have really kind of sensors. Without the sensors, you don't have a data. So the sensors are developing so fast. And I believe in your working time, you'll be dealing with quantum sensors. When you have the quantum sensors, you are in the different world. The amount of data will be produced with this new generation of sensors. Probably AI might be find difficult to do running. You can really check the earthquake, earth movement, anything. The second important thing, of course, hardware. Hardware is developing so fast. When you think of a hardware, in everything within the chip, in the chip, you've got transistors. Do you know how many transistors in chip these days? Any idea?
10 million. 10 million, that's it.
10 million? Billion.
Yes.
Actually, now it's getting to 50 billion in new version the chips. But it started from 100,000, a million scale, then a billion scale. Now it's going to 5. I saw some chip really 40-something billion. And of course, this is really going to, again, processing capabilities. That is a skill, using the available machinery. Now you can really make devices in the femtometer scale. So that is helping. The third one is algorithm. The algorithm is growing with the help of AI. So we've got an augmented route to improve the algorithm. The sixth one is the word. Word is needing that, real word adoption, because you can make money out of that. Of course, investments are growing in AI, and of course, with this, talents are growing. Probably, when you look at the classrooms, most of you say, okay, I will be doing something related to AI in my university life. This is kind of talent growing in the AI. And of course, the cloud and infrastructure help the growth of AI that fast. Now, this is the trick. Currently, we are in the artificial narrow intelligence, A and I. When I say this one, you say you've got voice assistant, recommendation system, autonomous system. This is still artificial narrow intelligence. And the second is AGI, artificial general intelligence. This is just coming to our life. The third one is artificial superintelligence. This is an unlimited scope, but purely hypothetical currently. But the second one start really learn and transfer, etc. at that stage. So this is the 3 level. All right? And how we can adapt those in your life? What are the maturity levels? Level 1 is automation, we said. Level 2 is data analysis. Level 3 is decision support. This is maturity levels of AI in our life. Level 4, semi-autonomous systems. Level 5, fully autonomous system like self-driving cars and things. And at the highest maturity level of AI, an autonomous decision maker will be AI. That is the bit problematic. When AI starts deciding autonomously without asking you anything, you have to stop there. So where I do stay in this position? And if AI capable of operating complex system independently within the defined objective and safety constraints. So what we are going to do in that roadmap? Okay, this 5 level we already discussed. How we can compare now human scientist and AI system? When does AI stop being just a tool? That's a big question. And become an independent driver and discovery and innovation? That's a big question. Could it eventually, AI, create new AI systems that are better than those created by us? Whatever we have been discussing so far on AI, we created it. Human being created it. And we start really having autonomous decision maker, innovation maker. So when AI become kind of, how you describe, I don't know, creator, I should say, and create better than you. And you don't need, really, and it is taking over, that means. Okay? This question is no longer theoretical. We all know AI very fast, taking a central role. Whatever you do now, you ask for AI. I don't know, you're young people meeting with each other, and when you meet someone, have you asked AI, do you think this guy is such and such? What do you think? Should I be a friend with him or not? You start doing that, or eating something, or coming here. You have to really be careful, really, asking everything. When I come here, I ask AI, how can I go there? I don't look at the map anymore. I don't check many things. This is getting real. Potential risks. That's what I like to discuss with the remaining time. One is a displacement risk. What I'm saying by that was raised as a question by one of you. Will AI replace some human jobs? Of course, artificial intelligence will take some of the tasks we do, and human workers will be out of job. For instance, there's a report by Goldman and Sachs. It says in the next decade, there will be 3 billion full-time jobs in the United States and Europe will be done by AI next 10 years. About 25% of current work tasks could potentially be automated. You won't be needing AI anymore. AI is no longer limited to simple repetitive tasks. When we think of, okay, we use AI in repetitive tasks, now AI starts thinking. AI starts really learning, reasoning, making decisions, writing, solving creative problems. Now AI is changing how we learn, create knowledge, solve problems, and use information. Really, we are different than 5 years ago. None of us learn as we did before. We don't have encyclopedias anymore on the shelves. Even we don't have books in our houses. All we have is screen and AI, and of course, all the information available. But the problem is, in the past, when you look at the encyclopedia, you trust very much the information there because you know it was screened and verified by authorities. Now you don't know. What's the most information you get from? Any idea? When you have any task, any homework, which sort of resources to use? Any idea? ChatGPT or other resources? But you don't know how reliable they are. Okay, the key question, I have those red bands in slides. The key questions, will AI replace human, or will human who how to use AI replace who don't use AI? That's a big question. We need to use AI. You don't say to your teacher, I have done it myself, this is my homework. And your friend says, okay, I have AI helping me and I have this. The quality will be like that. So who is going to replace who? Will AI replace me? Or when I use AI, I replace someone else? This is a big question. The second big risk, potential risk, dependency risk. Are we becoming too dependent on AI? Using AI can make our lives easier, solve a problem. In my time, you used to have a book of logarithms. We look at from the book, what is the logarithm of a number? Or we should know how to make a square root of the number. How many of you, without help of AI, have a number and have the square root of that in the class with your education. Go on, put your hands. Can you take a square root of a number without help of a calculator or AI? 3, 4. Not many, because we are dependent on the AI or depend on the calculators. So if you always rely on AI to think, make decision, and solve problem, we may gradually lose important skills such as critical thinking, independent decision making, problem solving, creativity, learning from our own mistakes. Third one is, which is quite important, commoditization work. When I say commoditization risk, I am thinking of commercially available AI. When all the tools and agents of AI is available for everyone, everyone uses the AI, how can I distinguish two people from each other, two companies from each other? Because if I am able to get a purchase any agent and put them together, make a generative AI, and I produce something, how can I compete with my competitors? So this is big risk of AI. How can you distinguish one student from other? If everybody using AI, asking the question, getting similar results, how can I know the difference between you all? How can I distinguish one of you from the others? AI commercially provide expert level information now. AI give the creative ideas. Writing and communication can be done by AI. And AI can solve problem. And AI give technical assistance. This, of course, makes harder to compete with each other, to stand out from the crowd. Please do read those red bands. I'm not going to read it up because of the time. So, what is the new paradigm? What should we do under those circumstances? We start from our everything, our knowledge, our everything, our skills. Our everything is our competences, and our qualification relies on that 3 pillars. So where are we with the area of artificial intelligence? What is the new paradigm? New paradigm is automating and augmenting many of our tasks by AI. It saves time, okay, no problem. Reduce our dependence on technical knowledge, skills, and competences. Transform our automating and augmenting many of our tasks, present an opportunity. So AI help us. AI makes things easier. AI makes us to feel more powerful. It's an augmented situation we have. You augment it. And it fosters human capabilities, AI, improve your capabilities, to rediscover human capabilities undervalued as inefficient, less productive. In schools, okay, your teachers or Sophocles spent really very good time how we are going to measure it. And when we measure something, AI can do it. But we ignore the other things, which is more humanly. So that's what we have to concentrate on, which is difficult to measure, of course. There's a time consuming to develop, and often overlooked because of they are expensive, they are time consuming, etc. So what they are, creativity. What they are, critical thinking. ethical judgment, emotional intelligence, collaborations, adaptability, and leadership. There should be the real area of education now to be concentrated because AI taken over other sides quite easily. Technical part, solving problems, and in most cases, we feel uncomfortable with those helps. But with these, that's what we have to concentrate and improve in students, in us. So a new paradigm is a hybrid framework for knowledge, skills, and competences. We should be discussing hybrid framework. Human strength and AI capabilities complemented and reinforce one another. That's the concept has been discussion over some time. A hybrid framework for knowledge, skill, and competences. So we have to master AI technologies. We have to learn machine learning, neural networks, their use cases, applications. We should do it. But we should integrate them with uniquely human knowledge, skills, and competences, which I try to list, but again, creativity, critical thinking, ethical judgment, emotional intelligence, collaboration, adaptability, and leadership. Okay. Can we compare those? Human intelligence, artificial intelligence, and decision-making. I have a limited time. I'm not going to read the slide, but this is quite important. I'll be sharing all those with you. But humans make decisions through reasoning, intuition, experience, and circumstantial judgment. AI makes decisions through data, algorithms, and statistical inference. The most effective decision, how we are going to make for the future, human judgment is complemented by AI-driven insights. When we compare the creativity of human intelligence and artificial intelligence, I don't have time to read all of it, but the red line says that the greatest innovation will emerge when human creativity is amplified, not replaced, with artificial intelligence. That's the big danger. When we replaced our abilities with AI, we have been done. So we have to really amplify, augment it. And learning, again, human intelligence, artificial intelligence, I try to compare. Human learn through experience, reasoning, and adaptation, as I already said. AI learn through data, algorithm optimization. So this is a different learning kind of things. The future of learning, combining human adaptability with AI's computational power. Because AI sources are really sources you put in the system. Okay, IQ. AI has a very large IQ compared to human. Because human is, IQ really is a logical reasoning, verbal comprehension, problem solving, abstract thinking. AI outperforms human by large because it has a pattern recognition, logical reasoning, mathematical problem solving, information retrieval, etc. So AI in IQ sounds like it's higher, but AI surpasses human in many IQ-related tasks, but human intelligence extends beyond IQ in common sense. AI doesn't have a common sense. Human has adaptability, ethical judgment, and ability to understand meaning and context. When I compare those different tasks, you can see I keep repeating the similar things, which is related to common sense, adaptability, ethical judgment, etc. AI is task execution As you can see, AI excels at the speed, scale, and consistency. They do it much, much better than us. But human, we excel at the adaptability, judgment, and handling the uncertainty. When you give the AI uncertainty, he's stuck. He gets here and there probably untrusted information and give you some wrong answers. But in uncertainty in human being, you start and think. Highest performance is achieved by when AI, again, augmented human capabilities rather than replacing it. Content creation, most of you prepare homework or any report, etc. But human create with purpose, experience, and emotion. When you write your homework, you know your teacher. You know how he is considering certain concepts. If you're writing on environment or animals, if you know that your teacher is love animals, you start really fulfilling towards that area. And the most exciting content produced when human creativity is enhanced by AI. Of course, the most important bit, emotional intelligence. As a human, we all experience emotion and empathize. But AI doesn't care. He does pattern, numbers, and that's it. So you've got some good thing in that. So emotional intelligence, one of the most distinctive strengths of human intelligence over AI. Please take this as very important message. Emotional intelligence, AI never replaced in the future. So please improve your looking at the word environment, animal rights, countries, policies, and whatever. Social cognition is another thing for comparison. Again, human understand people. When I look at the classroom, I can more or less understand who's feeling what, who's tired, who's sleepy, who wants to say, finish it, I want to go and eat, etc. AI don't understand that. AI continues. But give me for a couple of more minutes, I behave like AI. Okay. Trust building. This became several times under the discussion in this summer school. Trust, actually, sustainable trust in the area of AI, this is combining trustworthy technology with trustworthy human leadership. So without a human leadership, you cannot trust anything. Yesterday, one of the last speak in the morning says, okay, I do many, many times, then I really check myself, is it correct? So there's a leader of this project or this calculation or this use case. So it has to be combined, but human is always there. Perception, how we perceive the life. When you look at the teachers, you have some idea who is really trying to take approach to you in what way, who is really reaching you to understand you, your feelings or your appetite to learn, and who doesn't care, just talk about it like that. This is quite important in the perception of a group. If you will be really in different part of the world, different work, and you present yourself to something, and you have AI prepared report. But what is important, not the report content, what's important, how you deliver it, how you approach the group. Can you convince them by the content or by your behavior, by the way you explain it? This is quite important for perception. Oops. So the future belongs to hybrid intelligence, AI plus human intelligence. Success in AI era will not come from competing with AI in areas where it exists. When there is AI, try not to compete with AI. Because in technical part, collecting the information is much better than you. But what you have to do, you have to complement its capabilities with your strength, your human strength. That's what we are discussing. The challenge is not to choose between AI and human experience. The challenge is to combine the best of both in the new model of hybrid intelligence. Hybrid intelligence. This is the new paradigm. Okay, that is the cognitive hybrid skills and learning, decision-making, idea generation. I described that. I finished the time because of that. This is the behavioral hybrid skills in the new paradigm, which is executing familiar tasks, performing unfamiliar tasks, and innovation. And emotional hybrid skills, understanding emotions, trust building, inspiring and influencing others. There are now, you can feel, two kinds of skills. One is abstract. Sometimes we can call it intangible skills and concrete tangible skills. What are the abstract intangible skills? Difficult to define and measured objectively. I cannot really measure all of your feelings or all of your other abilities, human abilities. I can only really measure it when we live, sort of have some things together. We have to have experience. And these intangible skills are context-dependent and highly transferable. I don't know how you can really present yourself without doing any session with you. And this is developed gradually over the long periods. So we have to really concentrate in education on intangible skills. So we have to improve the students' ability in the intangible parts. And it's difficult to automate or replicate. My way of talking belongs to me. It's not difficult. It's difficult, really, to replicate someone else coming and talking like me. This is different. So this is intangible and closely linked to personality, values, and behavior.
Is it possible someone to imitate?
Imitation is never like as the original. But it is closely linked to personality, values, and the behavior, evaluated through observation and long-term performance, become increasingly valuable in the AI area. In AI area, in this period, intangible skills are much more valuable. And concrete, tangible skills you have to acquire, clearly defined and easily measurable, should be. Learn through the structured education and training. It should be task-specific, directly applicable, can often require relatively quickly, more susceptible automation AI, primarily based on the technical knowledge and procedures, assessed through the test, certification, and the objective performance metrics. So, when you put them together, you've got the concrete skills, you've got abstract skills. Where they intersect, that should be you successfully prepared for the future. Now, the important question is the third one, is the artificial superintelligence. We more or less sort of touched upon that. When the AI starts autonomously thinking, making decisions, innovating, and when AI surpasses you, what will happen? What's the danger? Okay, this is the potential for superintelligence to go gain control. AI system become more effective to accomplish assigned tasks easily, generate new things. And two instrumental sub-goals particularly important. Self-preservation. You know, when you say AI, AI needs power. When you take the power out, there's no AI. When AI starts really getting its own power, independently from you. So this is one of the important steps of super intelligence time. AI start self-preservation, maintaining their continued operation, avoiding shutdown. Well, there will be a period you won't be able to shut down the AI. It won't allow you in that period. And power acquisition, of course, obtaining additional resources, influence the capabilities to improve the likelihood of achieving assigned objectives. When AI needed power, AI will ignore you. You might be cold, you might not be cooking, but AI needs, I need the power. It will take all from you. Okay? And the superintelligent AI system could potentially find it easier to gain influence by persuading or manipulating the people. So the countries might say, okay, I need a super AI. It doesn't care what happens to my people, my energy, etc. AI might really persuade something, make them believe it will happen, it will be good for the country or their own country. This is the big problem, really, for the future. Such concerns base the possibility and highly capable of AI system for the future. Well, I finish with this slide, which is used by, I think, one of the guys who had a Nobel Prize, Tiger Cup analogy. In this analogy, humanity, we all do love animals, maybe like someone who has adopted an adorable tiger cub. Little tiger cub, very nice, you love it, you feed it, you clean it. And it's your pet. When the cub is harmless, when it's pet, when it grows a full or grown tiger, it could easily overpower its owner, you, and it can harm you. What can you do? This is your pet. You spend time, you nurture it, you feed it, and you make it grow. Now it's bigger than you, and it can kill you anytime. What can you do? This analogy says, get rid of the tiger before it becomes too powerful. Kill the AI. Can you do it? No. At this stage, we cannot do it. This is unrealistic. That's what we have to ensure, that AI will never harm us. AI will never harm human. How? By ensuring that increasingly capable AI remains aligned with human values, human goals, and human interests, and even it's more powerful, that humanly part will be under control over the years. This is the great challenge, not simply building more intelligent AI, ensuring that increasingly powerful AI systems remain aligned with us. I do thank you all. This is my last slide. In here, this is the one painting by René Magritte from Belgium. It says, the egg is there. What you paint is up to you. Thank you very much for listening to me. Any question I can answer.
So we talked about artificial superintelligence. In case that it surpasses human in almost every cognitive skill, what competencies will remain unique to humans, and how will the education system will need to be reshaped in order for young people to know how to deal with
Okay.
superintelligence?
That's one thing I've been really trying to cross to you. If you get a question, it should be clear on your mind. When you start reading, even you cannot control the words, and I'm trying to really understand the actual meaning. What you are asking is, what should we do for education system if AI is changing that way? That's the question, is it? Okay. Our good friend Sophocles has been really discussing on what we should do in physics. Or same goes for chemistry, sociology, maths, whatever. From the secondary school or before, really, we should start really improving the intangible part of human, which I explained you, to be able to sympathize with your friends, sympathize with your environment. You should be able to explain yourself, whatever you think of, and you should be really presenting things very often. I don't know whether or not in your education is quite available. For instance, education goes through the project-based education, in which you start really thinking with the help of AI, but your leader, your supervisor, really verifies how much you really put in. The good thing, after you prepare your report in the project, you start explaining yourself. If you are really just copied through AI, you cannot explain yourself. You should be really digested what you are trying to say and what you are believing in. Without believing in something, it's impossible to explain. You just convey. Conveying information and explaining information are different things. So in the education system, probably there should be most project-based, and checking your abilities in both sides. Of course, you do the technical side with the help of AI, or you augment it, but intangible part, AI doesn't help you very much. You, your friend, your teacher, your leader helps you. This should be more important in the educational combination. Thank you. You want a microphone?
Yeah. Hello. Well, my question is, how can we use AI to learn more about AI as teenagers?
Okay. It's like, how old are you? How old are you? Do you have a girlfriend? Do you ask your friend, could you tell me what you are, who you are, what you do? He tells you. Do you believe in them? Same goes with AI. When you ask to AI, AI tells you what AI is. But the trust is important part. Currently, we've got some problem with AI trust. And, you know, AI have hallucinations. AI get information everywhere. And some of them is really, really bad information. Some of them not reliable. So asking AI, but to check again yourself to understand AI. But when you say understanding AI, what do you mean is a big question. How you're going to use AI is a question.
My name is Stoicho. I'm 16 and I'm from Bulgaria. And my question is, in those stages of development of AI, which you were talking about, ANI, AGI, and ASI, when we as humanity are developing AI and approaching that superior intelligence, how can we make sure that, let's say imagine that we are at a general intelligence level, that some people don't make AI the modern day slaves, especially when now we are living in a capitalistic society worldwide, where work gets rewarded by currency and that currency is used for anything you want. How can we make sure that an American or Russian billionaire doesn't just buy robots or AI and use them to work, and to also kind of like put away that responsibility which humanity has or that certain person has over this AI to bring, in my opinion, like some kind of catastrophe?
Yeah, it's a complicated question, but let's think of you're in the sea. Have you done any travel on the sea?
Yes.
Open sea.
Yes.
If I ask you, where are we? What do? Look around. Say, okay, we are in the middle of the sea. And how far from where you want to go? How far from your parents? How far from your target? What you need is information. So information, as much as you can collect, gives you more or less your point where you are in AI. And once you are stuck, what do? Go to captain. Ask, because he's got a better information, more reliable information on the position of that ship. He says, okay, you're in middle of the sea, but far from so many kilometers from UK, so many kilometers from Greece, etc., etc. So this is like that, really. To see where are we in AI is like in the sea. We look at the information we've got and what's happening around us too. For instance, today, a friend just before me explained your regression to really some spots, etc. So this is machine learning. There's one information. The other friend explained something, and Sophocles explained how we can really change the actual understanding of the educational performance outcome using AI. These are all inputs. These inputs takes you where you are in AI journey. But in general understanding, actually we are still in the narrow AI. In generative AI, we are just we don't see many applications around us. Okay? Well, as I said, it's a complicated question to answer fully.
Yeah, it is, because we have to kind of imagine the future. I want to ask a question, just to clarify. I am kind of relying on our imagination for the future, but because there really isn't kind of anywhere else to go but to develop it again, so we can do it more efficiently, better. And again, it kind of is, like I think you said it, where we have to build or establish some kind of organization to keep track of our usage of AI, even today, because a lot of AIs are being misused. I know that there was this kind of controversy around generative AI, and it's how people are making it to use pornography. And I feel like that's what I was trying to get at.
Yeah, the actual message is you never replace yourself with AI. Of course, you use AI to augment your abilities. That means hybrid abilities, like hybrid knowledge, hybrid skills, hybrid competencies. Okay. I thank you once more to listen to me. Thank you very much. See you somewhere.
Thank you very much, Mr. Sener, for this great journey in artificial intelligence and the well-documented presentation. Thank you again. We'll close the ceremony now, the morning, and in a few minutes you can go for lunch to the restaurant.
lunch will be served at about half an hour from now. The next session will be started at 3:30. Meanwhile, after 3 o'clock, you may come here and give your presentations for tomorrow to Mr. Dimitris. Dimitris, stand up, he is here, so he can upload it with your USB sticks to this computer. 3 of you, the most, let's say, brave among all of you, will present now, not now, today, at 5:30. Is that clear? So, the program finished for the day 2 is 6 o'clock. After 6 o'clock, you may alert your parents to pick you up. Okay, get some rest. The one of you that has not complete the registration, you may complete it now. Outside of here is the gifts and the budgets. You may complete it. Thank you.